All right, let's continue. Um, so we last left off on this page. Let's read it. But things are a bit more complex. Turns out there's a problem. The head first gyms are expanding everywhere. Different countries that use different languages and different measures. For example, in England, the machines need to report information in kilograms and kilometers. So different units instead of I think pounds. What is it? Pounds, miles, and cows. It's kilograms, kilometers, and cows. The gyms have lots of different types of equipment. If they have 20 different types of machines and have gyms in 50 countries, that means there will be 1,000 different versions of the software. 20 times 50, I think. Yeah, that's a lot of different versions. And then there are other problems too. First, if an engineer upgrades the sensors used on a machine, she might need to upgrade the code that talks to them. If the displays ever change, the engineers might need to change the code that generates the output. Plus, there are many other variations. If you think about it, you get the same kinds of problems when you write any software. Different machines might require different device driver code, or they might need to talk to different databases or different graphical user interfaces. You probably won't be able to build a version of your code that will work on every machine. So, what should you do? It's time to genericize it. So, programs are made out of lots of pieces. You've already seen that you can build programs using different pieces of object code. You've created .o files and .a archives, and you've linked them together into single executables. Raisins, flowers, butter, anchovies. So this is actually anchovies not might not be bad, salty and sweet. Okay, anyway, but once they're linked, you can't change them. So the problem is that if you build programs like this, they are static. So if you were to just build the program with all your headers and C files together all the time, they're not really reusable. So they're saying that once you've created a single executable file from those separate pieces of object code, you really have no way of changing any of the ingredients without rebuilding the whole program. So the way we've always been building programs, essentially. The program is just a large chunk of object code. There's no way to separate the display code from the sensor code. It's all lost in the mix. So it's time to create libraries. Wouldn't it be dreamy if there were a way to run a program using switchable pieces of object code? But I guess that's just a fantasy. Dynamic linking happens at runtime. The reason you can't change the different pieces of object code in an executable file is because, well, they are all contained in a single file. They were statically linked together when the program was compiled. But if your program wasn't just a single file, if your program was made up of lots of files, separate files that only joined together when the program was run. So instead of compiling with your libraries, we're going to bring in the libraries at runtime. We're going to access library code at runtime instead of compiling with all our library code into one executable. So I guess think of your executable as sort of like an entry point and kind of like a centralized thing where it just like calls separate services. Um, so that's the dynamic part of it. Okay, so if your program wasn't just a single file, if your program was made up of lots of separate files that only joined together when the program was run, you would avoid the problem. The trick then is to find a way of storing pieces of object code in separate files and then dynamically linking them together only when the program runs. So that's key. Dynamically linking them together only when the program runs. And you just store bits of it, like maybe like references to them. So this way, you'll have these two here, like corresponding to sensor, these two corresponding displays, and you can kind of mix and match on runtime. So when your program runs. So can you link a .a file at runtime? So remember those archives that we were creating, those lib xyz.a libraries? So whenever we actually compile, we were compiling them statically, I think. So that's why they were always coming in as like one executable. But now it's like we want to actually bring in different code whenever we run the program, not compile the program. So how do we access all that object code in another library while we're running the program? So I think that's what they're trying to say at runtime. So yeah, I want to make that distinction. It's a very important thing, dynamic versus static. So dynamic is you're tapping into code at runtime. Static is when you're actually bringing in that code and putting it into that exe. Yeah. So you need to have separate files containing separate pieces of object code, but you've already got separate files containing object code, the .o object files and the .a archive files. Does that mean you just then need to tell the computer not to link the .o files until you run the program? Sadly, it's not that easy. Simple object files and archives don't have quite enough information in them to be linked together at runtime. There are other things our dynamic library files will need, like the names of the other files they need to link to. Dynamic libraries are object files on steroids. Okay, so dynamic libraries are similar to those object files that you've been creating for a while, so similar to those .o files, but they're not quite the same. Like an archive file, a dynamic library can be built from several .o object files, but unlike an archive, the object files are properly linked together in a dynamic library to form a single piece of code. So like an archive file, a dynamic library can be built from several object files. So same thing like an archive. An archive consists of several object files, but the difference is that the object files are properly linked together in a dynamic library to form one big object code. So like if we were to go back and look at the archive, how the structure of an archive looks like, .a, right here, you see how there are separate object files. So like if you created a .a file, it will just, out of like multiple .o files, it just kind of throws them and wraps them up together, kind of like just throwing things into a bag. And that like these .o files aren't aware of each other. They're just separate. And your code just basically compiles with them and stitches it all together. But with the dynamic version, these .o object files become interconnected with each other. They're aware of each other and assemble to the point where you can actually start running that code. So that's why it says that those multiple object codes become one big object code. So hopefully that makes sense. So how do you create your own dynamic libraries? Let's see. So first, we need to create an object file. If you're going to convert the hfcal.c code into a dynamic library, then you need to begin by compiling it into an object file like this. So remember to do the includes because we have an includes folder here. And then fpic, I have no clue what that means, -c with the C file, and then -o with the object file to specify the object file. So remember, -c means to compile, but don't link. And what does fpic mean? Let's see. Did you spot the difference? You're creating the hfcal.o exactly the same as before, except you're adding an extra flag, -fpic. This tells GCC that you want to create position P independent I code C. Position independent code, fpic. Some operating systems and processors need to build libraries from position independent codes so that they can decide at runtime where they want to load into memory. So Position independent code essentially means that it doesn't matter where this code loads, like what address it loads into memory. Your code will always be like somehow be able to access that code uh, when it's running. So it's not like fixed in this case. And whereas like something that's statically linked, that code, those object files are kind of placed like in a hard coded position in memory whenever you run your program. Your program knows like exactly what memory addresses they are, I believe. Okay. Yeah, see, position independent code can be moved around in memory. Okay. So now the truth is that on most systems, you don't need to specify this option. So that's an interesting thing we're gonna have to ask ourselves is like, well, then how does our program actually access this position independent code? Because if it's always like moving around, like when you start it up, when you run your program, that position independent code, the dynamic library is going to be elsewhere in one instance and in another place in another instance. So uh, when I say place, I mean like memory addresses. Try it out on your system. If it's not needed, it won't do any harm. Okay. Anyway, so what is position independent code? Position independent code is code that doesn't mind where the computer loads it into memory. Imagine you had a dynamic library that expected to find the value of some piece of global data 500 bytes away from where the library is loaded. Bad things would happen if the operating system decided to load the library somewhere else in memory. If the compiler is told to create position independent code, it will avoid problems like this. Some operating systems like Windows use a technique called memory mapping when loading dynamic libraries. This means all code is effectively position independent. If you compile your code on Windows, you might find that GCC will give you a warning that fpic option is not needed. You can either remove the fpic flag or ignore the warning. Either way, your code will be fine. Okay. So what you call your dynamic library depends on your platform. Dynamic libraries are available on most operating systems, and they all work in pretty much the same way, but what they're called can vary a lot. On Windows, dynamic libraries are usually called dynamic link libraries, and they have the extension .dll. On Linux and Unix, they're called shared object files .so, and on the Mac, they're just called dynamic libraries .dylib. But even though the files have different extensions, you can create them in very similar ways. So it's just different extensions, but conceptually they're all the same. The shared option tells, right here, gcc-shared, tells GCC that you want to convert a .o object file into a dynamic library. So we're converting this hfcal.o file into a dynamic library. It will store the name of the library, and just to remind, hfcal is this one here. It's a generic printing function that just has display calories. Okay, so that will be shared. Okay, where was I? Okay, yeah, it will store the name of the library inside the file. So if you create a library called libhfcal.so on a Linux machine, the libhfcal.so file will remember that its library name is hfcal. So why is that important? It means that if you compile a library with one name, you can't just rename the file afterwards. So it's like hard coded into the dynamic library. If you need to rename a library, recompile it with a new name. Wow. Okay. So compiling the elliptical program. So let's do this. GCC-shared. Okay, we need to first compile it into I guess a .o file. And this one means to create the position independent code. So we're creating a different version of a .o file. It's like a normal, like It's the normal way of creating a .o file, except with the fpic, we're saying that this .o file that's going to be generated is position independent. So inside that .o file is going to have all that logic necessary to make that happen. So first, let's compile hfcal.c into that position independent object file. So we'll specify the includes directory that we want. We're going to do fpic -c hfcal.c-o hfcal.o. Huh? What's going on? -i. Is it like this? Oh, it's like that. Okay. Well, this is wrong. It's current directory slash. Okay. LSLA. So we'll have the position independent code here. And then what we need to do is we need to do this, which is basically turn this into a .so file. gcc-shared hfcal.o-o. Missing file name. Oh. lib hfcal.o. so, which is what we're supposed to specify. And then we cannot just like rename with mv command. We have to like recompile if we want to have a different name for our library. So let's do this. Okay, lib hfcal.so. Okay. Oh, it should be in libs. Let's move it there. mv lib hfcal.so to libs. Okay. And let's look at what's in libs. Okay, cool. So it's automatically knowing that it's executable. That's okay. Okay. Now we compile the elliptical program. Sure. Once you've created the dynamic library, you can use it like a static library. So you can build the elliptical program like this. Okay. So now we're going to build with the .so instead of the .a. Let me remove the .a just to see. So rm libs hfcal.a. Oops. Just in case. Yeah, I don't want to accidentally make this work. So then what we want to do is we're going to compile our elliptical.c into an object file called elliptical.o. Okay, so that's the first step. And make sure you specify the include directory. So for me, it'll be includes -c elliptical .c-o elliptical.o. Okay. Next, I want to link my elliptical.o with the lib hfcal.so and output that into the elliptical program. Before I do that, I'm going to delete the elliptical program. So now I have nothing here. Okay. So I'm going to do gcc elliptical.o-l libs. So that's where my dynamic library lives in. And then I'm going to do -l hfcal, include that, -o elliptical. Huh? Uh-oh. Again, one of these. Wait, were we supposed to also include the .a? Did I mess up? Let's see. Oh, user bin ld cannot find -l hfcal. Is it because of the / thing again? Okay, this book messed up again. Okay, so it's current directory / Okay, we're good. We have it. I think I fell for that last time too. Okay, so error while loading the shared libraries. Lib hfcal.so cannot open shared object file. Okay, so I guess there's a caveat to this. Okay, you've created a dynamic library in the /libs directory and built the elliptical test program. Now you need to run it. Okay, because hfcal isn't in one of the standard library directories, you'll need to make sure the computer can find the library when you run the program. So on a Mac, you can just run the program. When the program is compiled on the Mac, the full path to the lib/hfcal.dylib file is stored inside the executable. So when the program runs, it knows exactly where to find the library. Okay, but on Linux, it's different. We're gonna get this error. We need to specify the to tell where to find the dynamic library when you run the program, because this program itself doesn't have that information to go to the code that is in the dynamic library. You have to specify the directory, or at least the path to find the .so file. So on Linux, that's not quite what happens. On Linux and most versions of Unix, the compiler just records the file name of the libhfcal.so library without including the path name. That means if the library is stored outside the standard library directories like /user_lib, the program won't have any way of finding the hfcal library. To get around this, Linux checks additional directories are stored in the ld library path variable, so a shell variable. Okay, so you can actually edit your bash shell, like bash rc, to include additional paths in your libraries, and then it'll be able to find it. Okay, so let's do that. Let's actually just do export ld. No, you know what? Let's not export. Let's just do it like this. ld library path, and then let's do .libs like this, ./libs. So we're setting an environment variable to say look into the ld library path that has ./libs, but we also need to append the current one so it can find other stuff in case we have things in other directories. And we'll use this to append. Okay, and then we run our program right after, so ./elliptical, and it works because we custom specified the path ld library path to also include not only whatever we have currently, but also the ./libs, the current directory libs. So current directory /libs right here, which contains hfcal.so. So that works. So yeah, and on Windows, it's what? It'll look for the current directory. Okay, so now let's take a look at how the code runs. I've been compiled using Cygwin and MinGW versions of GCC compiler. So both compilers create Windows DLL libraries and Windows executables. And just like Linux, Windows executables store the name of the hfcal library without the name of the directory where it's stored. So Linux and Windows are the same when it comes to this. But then Windows doesn't use the ld library path variable to hunt the library down. Instead, Windows programs look for the library in the current directory, so the current directory of where you're running it. And if they don't find it there, the program search for it using the directory stored in the path variable. Okay, so this is the equivalent. Interesting. Okay. And if you've compiled the program using the MinGW compiler, you can run it from the command prompt like this. So, sure. I don't use Windows, so I can't tell. Yeah, so doesn't this seem a little complex? It is, which is why most programs that use dynamic libraries store them in one of the standard directories. That means on Linux and the Mac, they are normally directories in usr_lib or usr_locallib, and in Windows, developers normally keep the .dll stored in the same directory as a executable. So if you're writing a C program with like a dynamic library, it's best to have like an installation script that will like copy your .so file to your usr_lib or usr_locallib directory. Or you can just tell people to just do the ld library path thing and hope all's well. Okay. So the guys at the Head First Gym are about to ship a treadmill over to England. The embedded server is running Linux and it already has the US code installed. So the tech guys installed the library in USR local lib, and here it is right here. And these are all other examples of libraries. This machine also has a header file for the hfcal library installed in USR local include. So you also need the header file so that your code knows how to call the functions. It needs to be declared. You can't call functions are undeclared, otherwise your compiler will assume you mean like an int function. If you can remember back to our whole exercise with headers. Yeah. The tech guys like to install libraries using these directories because it's a little more standard. The machine is all configured for use in the US, but things need to change. Sure. The system needs to be updated for use in the gym it is being shipped to in England. That means the treadmill's display code needs to be switched from miles and pounds to kilometers and kilograms. Okay? And this is the hfcal underscore uk.c. Okay? The software that's already installed the machine needs to use this new version of the code because the applications connect to this code as a dynamic library. All you need to do is compile it into the USR local lib directory. Assuming that you're already in the same directory as the hfcal.uk.c file and you have written permissions to all directories, what commands would you need to type to compile this new version of the library? Well, first, we had to build the object file, and then we had to use that object file and create a .so file. And then we had to compile our program with that .so library path specified and the exact library. And that's it. Okay. If the treadmill's main application is called /opt/apps treadmill, what would you need to type in to run the program? I guess we'll do the /opt/apps treadmill, and then we can just run it with yeah, we just do that because if the LD library path is in the standard paths, it should be fine. But I think we don't need to include the includes path because it's already in the standard path. The library is also in the standard path. So we could just do the full path to the program. We just do /opt apps treadmill. So let's see. So yeah, compile it, the object file with fpic, and then compile the so file, and then we just run it. See, you don't need to set the LD library path variable because the library is in the standard library directory. Yeah. So did you spot that the library and headers had been installed in standard directories? That meant you didn't have to use a -i flag when you were compiling the code. And you didn't have to set the LD library path variable when you were running the program. So yeah, just remember to do this. If it's not in the standard library directory, you have to always specify this when you're running your program. Or you can put it into the bash RC. At the same time, when you distribute your program, you also have to put this in as like a direction or something. Or just have a script that will copy it all into the standard library directories. So Linux can be crazy sometimes. That's the reason why I guess some people use a Mac, because it's just easier. So now that you've updated the library on the English treadmill, let's try it against an American machine. This is one of the unaltered US treadmills using the original version of the libhfcal.sol library. Okay. The treadmill application starts when the machine boots up. So after using the machine for a while, the display shows up like this. Okay? The treadmill program on the US machine is dynamically linking itself to the version of the hfcal.sol library that was compiled from the US version of the hfcal program. But what about the treadmill in England? Let's see. So we have the same treadmill program, but now we're going to use hfcal from the UK library. So the English machine has the same. Is this the same person? Oh, it's different people. the English machine has the same treadmill program installed, but on this machine, you recompiled the libhfcal.sol library from the source code in the libhf or in the hf_uk.c file. When the runner has been on the treadmill for a similar distance, the display looks like this. So kilograms, kilometers, and calories. Cool. So it worked. Even though the treadmill program was never recompiled, it was able to pick up the code from the new library dynamically. Dynamic libraries make it easier to change code at runtime. You can update an application without needing to recompile. If you have several programs that can share the same piece of code, you can update them all at the same time. Now that you know how to create dynamic libraries, you've become a much more powerful C developer. Totally agree. All right, fireside chats. Let's go. Tonight's talk. Two renowned proponents of modular software discuss the pros and cons of static and dynamic linking. Static. Well, I think we can both agree that creating code in smaller modules is a good idea. Absolutely. It makes so much sense, doesn't it? Yes. Keeps the code manageable. Yes. Nice large programs. Large? Yes. Nice big programs with their dependencies fixed. So everything inside, one big executable. That doesn't sound like a good idea. What do you mean, old friend? I think programs should be made up of lots of small files that link together when the program is run. That's but no, seriously. I'm being serious. So, more modular. Bring them in as you need it. What? Lots of separate files joined together willy-nilly? I prefer the term dynamically to willy-nilly. But that's a recipe for chaos. It means I can change my mind later. You should get things right in the first place. That's not always possible. All large programs should use dynamic linking. I guess so. All programs? Oh, I think so. I just said that. What about the Linux kernel? That large enough? And I believe that's statically linked. Yeah, I know that's your one. Okay, statically linking might not be as loose and formal, but you know what? Static programs are simple to use. Single files. Want to install one? Just copy the executable. No need for DLL hell. So again, static programs are the programs that we've been developing all this time. That's why they've always been like one easy executable to run. Look, we'll just have to agree to disagree. I can't change your mind? No. So you're telling me your mind is statically linked. Huh. So important points. Dynamic libraries are linked to programs at runtime. Dynamic libraries are created from one or more object files. On some machines, you need to compile them with the fpic option, and fpic makes the object code position independent. You can skip fpic on many systems. Windows. The shared compiler option creates a dynamic library, so gcc-shared. Dynamic libraries have different names on different systems. Life is simpler if your dynamic libraries are stored in standard directories, and otherwise you might need to set the path if you're on Windows, and LD library path if you're on Linux. Very cool. So there are no dumb questions. Why are dynamic libraries so different on different operating systems? Operating systems like to optimize the way they load dynamic libraries. So they've each evolved different requirements for dynamic libraries. I tried to change the name of my library by renaming the file. Don't do that. You gotta recompile it. But the compiler couldn't find it anymore. Why not? When the compiler creates a dynamic library, it stores the name of the library inside the file. If you rename the file, it will then have the wrong name inside the file, and it will get confused. If you want to change its name, you should recompile the library. Why does Cygwin support so many different naming conventions for dynamic library files? Cygwin makes it easy to compile Unix software on a Windows machine. Because Cygwin creates a Unix-style environment, it borrows a lot of Unix conventions. So it prefers to give libraries a .a extension, even if they're dynamic DLLs. Are Cygwin dynamic libraries real DLLs? Yes. Because they depend on the Cygwin system, you need to do a little work before non-Cygwin code can use them. I don't think anybody really uses Cygwin in real life anymore. I think people are using Windows subsystem for Linux now. And even then, I don't think people are using MinGW too. Why does a MinGW compiler support the same dynamic library name as format as Cygwin? Because the two projects are closely associated and share a lot of code. The big difference is that MinGW programs can run on machines that don't have Cygwin installed. Why doesn't Linux just store library path names in executables? That way you wouldn't need to set the LD library path. It was a design choice. By not storing the path name, it gives you a lot more control of which version of the library a program can use, which is great when you're developing new libraries. Oh, that's true. It's like pluggable. You can swap out a new version, with an old one. That's so cool. I didn't realize that. Why doesn't Cygwin use LD library path to find the libraries? Because it needs to use Windows DLLs. Windows DLLs are loaded using the path variable. Which is better, static or dynamic linking? It depends. Static linking means you get a small, fast executable file that is easier to move from machine to machine. Dynamic linking means that you can configure the program at runtime more. If different programs use the same dynamic library, does it get loaded more than once, or is it shared in memory? Ooh, good question. Basically, if I had two different programs, and they both use the same library, the same .so, does it get loaded more than once, like one copy for each, or do we share it? Interesting. That depends on the operating system. Some operating systems will load separate copies for each process. Others will load shared copies to save memory. That's very interesting. I don't know what Linux does. Are dynamic libraries the best way of configuring an application? Usually, it's simpler to use configuration files, but if you're going to connect to some external device, you'd normally need separate dynamic libraries to act as drivers. Cool. And we're done with this chapter. What's next? OpenCV. Let's skip this one because it's another one of those projects that are probably dead now. Like, and not OpenCV, but like the links and stuff at this point. So, move to chapter 9 and processes and system calls. Wow, we're gonna go to advanced stuff. Wow. Okay, so I'm gonna stop here, and wow, we're pretty far. 1, 2, 3, 4. Pretty much 4 more chapters, and we're done with the book. And you can see the scroll bar down here. Made a lot of progress. All right. Thank you. See you next time.